So the first property is linear property. So what is the linear property of Laplace transform? Suppose we have given two functions f1t and f2t, and its Laplace transforms are f1s and f2s respectively. So in that case, Laplace transform of the combination of this f1 and f2 in such a way c1 f1t plus c2 f2t, that equals to c1 Laplace transform of f1t and c2 Laplace transform of f2t. So this is the basic linear property of the Laplace transformation, where c1 c2 are any arbitrary constants. So let's see the proof of this linear property of Laplace transformation. Here we have given Laplace transform of f1t is 0 to infinity e to the power minus st f1t dt, and Laplace of f2t is 0 to infinity e to the power minus st f2t dt. It is defined as L1s and F2s from the definition we have taken. Now, by considering the c1 and c2 arbitrary constant, we take the left LHS, that is Laplace of c1 f1t plus c2 f2t. According to definition, it is 0 to infinity e to the power minus st c1 f1t plus c2 f2t dt. So now we use the integral operator, and as we know, integral operator is linear, so it becomes c1 0 to infinity e to the power minus st f1t dt plus c1 integration from 0 to infinity e minus st f1t dt. So again we use the definition of Laplace transformation. By using Laplace transformation, we get this RHS, which is quite simple to prove it here, and on the basis of this linear property we can see some examples also. Now let's see first the generalization of the linear property. Earlier we had taken the two function f1t and f2t. Here we are generalizing fit, where I is equals to 1, 2, 3, 4 up to n. So in the general case, Laplace of summation of ci fit, that equals to summation of ci Laplace of fit, which is quite easy to prove it. Now in this section we will see the another property of Laplace transformation, that is first shifting property. It is defined as if the Laplace of ft is fs, then when we multiply ft by e to the power at, it shifts the s by minus a. So the Laplace of e to the power at ft is what? F of s minus a. How we prove this? As we know that the Laplace of ft is 0 to infinity e to the power minus st ft dt. According to definition we have, so we apply here the left hand side, Laplace of e to the power at ft, that equals to 0 to infinity e to the power minus st, and in the place of ft we write e to the power at ft dt. So it becomes e to the power minus s minus a t ft dt. Now we take here u is equals to s minus a, which is greater than 0, because s is greater than 0 here. So it becomes 0 to infinity e to the power minus ut ft dt. Now it is again in the form of Laplace transformation. So it is, we can write f of u, and what is u? U is s minus a, so finally it is f of s minus a. Similarly we can write it here, if Laplace of e to the power minus at ft is given, then it will be f of s plus a. So this is known as first shifting property of the Laplace transformation. This is very useful property by handling the some Laplace transform of some functions. Now come to the next property of Laplace transformation, that is second shifting theorem, or second translation we say. Let Laplace transform of ft is fs, and we define the function gt in such a way, gt is equals to f of t minus a when t is greater than a, and 0 if t is less than a. then the Laplace transform of gt is e to the power minus as fs, where fs is Laplace transform of ft. To prove this, first we use the proper definition of Laplace transformation. So the Laplace of gt will be what? 0 to infinity e to the power minus st gt dt. As we know, the Laplace of, by definition of Laplace transformation. Now, as gt has the two value f of t minus a and 0, so we split the limit 0 to infinity between 0 to a and a to infinity, and we put the value of function gt. From 0 to a it is 0, so the integral is 0. Now finally it is a to infinity and e to the power minus st ft minus a dt. Here we substitute here t minus a is equals to p, so that what we get, dt is equals to dp, and the limit will be, for t is equals to a, p will be 0, and for t is tends to infinity, then p will also tends to infinity. So our limit will be 0 to infinity. The Laplace of gt will be 0 to infinity e to the power minus s p plus a fp dp. E to the power minus sa we take outside, and we have the rest part of integral, that is 0 to infinity e to the power minus sp fp dp. So we compare with the Laplace definition of Laplace transformation, and we get here e to the power minus sa fs. Thus the second shifting property is proved. Now we see here another property of the Laplace transformation. If Laplace of ft is fs, then Laplace of f of at is 1 upon a f of s upon a. This transformation is very useful when we apply the inverse Laplace also. So in that case, Laplace of f of at we can write 0 to infinity e to the power minus st f of at dt. Now we put here at is equals to x. So it becomes 0 to infinity e to the power minus of sx upon a fx dx upon a. So finally it is 1 upon a 0 to infinity e to the power minus sx upon a fx dx. So 1 upon a comes out in the right hand side. Only we required to prove it f of s upon a. Rest part should be f of s upon a. So that's why we put it here, t is equals to x. What we get? 1 upon a 0 to infinity e to the power minus st upon a ft dt. Now we replace it s upon a by p. So our integral will be 1 upon a 0 to infinity e to the power minus pt ft dt. Now it is in the form of what? Laplace transform. So that we can write here 1 upon a f of p, and as we know p is what? S upon a. So finally we get the right hand. Now come to next property of Laplace transformation. It is Laplace transformation of derivative, ordinary derivative. So if Laplace transform of ft is fs, then we can define the Laplace transform of nth order derivative of ft, that is f of nt, fnt. It is equals to Sn fs minus Sn minus 1 f0 minus Sn minus 2 f dash 0, and so on. We get at the last Fn minus of Fn minus 1 0. If we put here n is equals to 1, then it will be Laplace transform of first order derivative. So it will be L f dash t is equals to S fs minus f of 0 only, and the rest term we can neglect here. So come to the proof of this property of Laplace transformation. So Laplace of ft is fs. So in the place of ft, if we put f dash t, so by the definition of Laplace transformation, it will be 0 to infinity e to the power minus st df upon dt dt. So it is e to the power minus st ft. Here we have used the integration by part. So in the first part, if we put minus infinity, then it will be 0, and if we put here t is equals to 0, then it will be minus of f0, and the rest is second part of the integral will be s of fs. So we simplify it and we get it. Laplace of f dash t is what? S of fs minus f0. So this is the Laplace transform of first order derivative. Now we extend this property to the second order derivative. For this, what we do here, we put Laplace of g dash t will be what? S and Laplace of gt minus g0 from equation 1. Now we put here gt is equals to f dash t. So it will be Laplace of f double dash t, that equals to s Laplace of f dash t minus f dash 0. So using equation 1, Laplace of f dash t is what? S fs minus f0. So finally what we get, it is s square fs minus s f0 minus f dash 0. Thus we get the Laplace transform of the second order derivative. So we can extend it and generalize using equation 1 and 2. We can generalize for nth order derivative. This is the Laplace transform of nth order derivative of nth order derivative of ft. This property is very useful for the solution of ordinary differential equations. So thank you for watching this video. Do not forget to subscribe my channel for more update and more videos related to mathematics, engineering mathematics. Thank you.